Today, I would like to talk a little bit about the embodiment or embodied intelligence in the domain of soft robotics. I want to show a little bit on the how we can translate from like morphological computations into neural computation and combine them together to have really like embodied neural control. So here is the I think this is like the general pictures of embodiments. Which has been shown during the conference several times. In these pictures, you have brain, body, and environment. And of course, you have the mechanics and sensor feedback, right? If we try to bring these frameworks into the soft robotics, we can see that in the middle part, which is the body parts, we can consider this as the morphological computations. In soft robotics, researchers have used different techniques by introducing, for example, different structures, different materials, such that to achieve the complex behavior in soft robots. Okay. Basically, in this case, you see the interaction between the robots and the environment in this loop, like the prefix or this body and environmental interactions, right? And the command that control the robot basically use mostly like basic simple open loop control. However, there's some works that you can bring this kind of smart material that can respond to different environmental simulations into this loop here, where the material can respond to, for example, light, heat, or solvent, such that it can exhibit like the reactive behavior here. In this part, we can consider this as the first level of the morphological adaptations, which consists of, like the structural design and smart material design or implementation for robots. On top of this, we can see another loop here where you have the sensor feedback go through the control, and the control or control computation in this case can reactively, according to sensor feedback, generate the behavior or even adapt the control parameters of soft robots. Like in this case, the robot can adapt the printing setting for growing the robot along the tube, for example, or one can use, for example, data-driven control approach to learn the model of this and then translate this, learn the model to the other type of robots. So this has been start to, implement in soft robotics little by little by using from model-based control to the machine learning or data-driven control. So in this case, we can consider this as the second loop or second level of adaptation by adapting the control parameters with sensory feedback. Okay, now we have two levels of adaptation here. So the problem here is that I think this is also is a general problem of robotics, that if the robot extremely rely on the sensory feedback, it could have a problem when we get the intermittent sensory feedback loss. For example, when the robot performs some behaviors and then there's some noise or feedback, or the sensor feedback gets no response for a certain period of time. Furthermore, the robot should be able to understand and recognize its abnormal state and even dealing with unseen situations. So this has not been completely implemented in soft robotic domain. And today I would like to elaborate on this more and to present our recent works on the embodied neural control with online learning and short-term memories to address these three features and to share with you today. So in this case, we have under this embodied neural control and learning, we deal with the upper loop here, the purple one here. And interestingly, by exploiting the embodiment effects of the soft body, we obtain the other loop here where you get the response from the environmental shape the body of the soft robots. And because of the body of the soft robot chain, it introduced to another type of prediction errors to change the control parameter to let the robot adapt to the situation accordingly. So let me go further. Here is the first case that we start to address this problem. How can we develop this type of embodied neural control with learning and memories into soft robot? We start from very simple robot by using this kind of simple soft actuators. And our point here is that we just want to look at, is it possible to make this simple soft single actuator soft robot move by using just, like one actuator, like a tube running back and forth, or the pressure running back and forth. To make this guy move, we look at how the worm claw, and we found that the worm show interesting behaviors. Like first thing, it perform like asymmetry body bending. The second thing, it has the little claws here to perform like the gripping to the surface or substrates. So according to that, we look into this implementation of verb-inspired morphological computation into this soft simple structure here. This is the work done by my former PhD student. He's just graduated now to become a doctor, Dr. Naris. So we implement three things into this robot. The first thing is that we make this robot bend in the asymmetric way. Like in this case, we make the head of this robot more sensitive. This means that when the air flow in here, the body will, blow up more. And by doing that, you have more concentration force at the front, such that the robot can have a better gripping force here. The second part is that we introduce these kind of sawtooth-like structures, the lamella structures, to have a good grip, and then it can also slide forwards. So by combining these, we can obtain like the mechanical interlocking when you put this robot on the rough surface, or the adhesive force when you put this robot on the flat surface. So this is about the basic morphological computation set up for our soft robot for further developing the neural control. The second part is here, we introduced the modular neural control, which consists of three main networks. And according to that, we have two sensors into this robot. One is the body sensors, which is we introduce the flex sensor inside the body. The second one is exteroceptive sensor, which is the laser sensor here on top of this robot here. By doing this, we have these three main modules. The first module, or center pattern generator here, perform like the open loop oscillators. By having this center pattern generator, you can have low or high frequency behaviors here. Low frequency, the robot perform large amplitude, and low frequency perform lower amplitudes. By having this set up, the robot can claw without any sensory feedback. Because of the morphological computation here, it can claw on the different substrate like flat and rough. The problem here is that when we let the robot claw on this kind of slope, and when it comes to this end, you see that the robot cannot sense the environment. It just falls down. And the nice thing of soft robot is it doesn't break because it's soft. The question here is that how can we let the robot learn and understand these abnormal states when it has no the ground? It should be able to adapt accordingly. To do that, we introduce the second network, which is, in this case, we call the forward model. This network basically translates the center pattern generators into the expected sensory feedback here through the blue line here. And we use the actual sensory feedback from the body to compare the expectation here through the comparator here. If the robot moves in the normal states, the error will be low, then you don't need to change the frequency of CVGs. And as soon as the expectation and the actual mismatch, you adapt the frequency here. And then this is how we learn the model of this reservoir computing feed-forward of forward model here. By doing this, in this situation now here, let me stop the video here. The robot has strong body bending because of the gravities and because of the softness. And this leads to the error or prediction error into the soft sensors in the body. According to that, according to the error predictions, then we use this error feedback to change the locomotion by stopping the robot from falling down. And this robot can also perform, like navigate into the narrow space. When in this case, it comes to the edge, it's adapt the frequency to the higher frequency, and then it can still continue to navigate on that. This is also another case where the robot, try to claw and then we lift it up, and because of the sensors bend and because of the body and the sensor bend, it introduced the error feedback or the prediction errors to stop the robot. The last part here is that when the robot claw and when you put the object on top of these robots, this robot will touch the ceiling, but this doesn't introduce the strong perturbation to the system that the sensor feedback here doesn't change significantly, then the error prediction cannot change the behaviors. To do this, we introduce exteroceptive sensor feedback like infrared sensors together with the Habian-like learning mechanism. And we learn this online to correlate between the sensor feedback and the output of the learning control. In this case, the robot can learn to obtain this sensor feedback and then adapt its locomotion online. Additionally, by using this setup here, is also this neuron act as the short-term memories to let the robot maintain this missing sensory information for the longer period of time, such that it can maintain the clawing behaviors in the high frequency. I will skip this slide. The equation there. So to sum up, what I want to share with you today is basically we introduce the center pattern generator as open loop control. We copy the center pattern generator to the forward model and compare it with the green line here, which is the actual feedback as the comparators. And then if there's some errors, we adapt the frequency of the center pattern generators. And that is the neuron adaptation parts. And the first part is about the morphological adaptation here. So I think with this, I would like to stop my talk now, and I would like to thank our collaborators and also my former PhD student, Dr. Naris, who contribute on all this work. Thank you for your attention.